In this example, we have two propositions, P and Q. We are going to look at the logical implication truth table for P implies Q. We look at proposition Q and its values are 0 or 1, and we write down its values alternating one step at a time. So we write down 0, 1, 0, 1. We write it down 4 times. For proposition P, we write down its values taking 2 steps at a time. So we write down 0 twice and 1 twice. So altogether we have 4 combinations that the values P and Q can take. We have 2 possibilities for proposition Q and another 2 possibilities for proposition P. So in total we have 2 multiplied by 2, or 4 ways we can combine the values of P and Q. So we have 4 rows in this truth table. The implication operator is false only when P is true and Q is false. So we have a 0 here. Otherwise we have true values. So we have 1s for the other possibilities. So you can just think of the number 100. That's the only exception to P implies Q being true. Let's look at the truth table for P implies Q plus P bar. There are 2 propositions P and Q in this statement. So we take one of the propositions, say Q, and we write down its values alternating one at a time. So 0, 1, 0, 1. And then we take P and write down its values alternating 2 at a time. So we have 2 zeros followed by 2 ones. In total we have 4 possibilities. Again, it's 2 by 2 is 4, just like for this first table. We need P bar, which is the negation of proposition P. So we look at the value that P has and we negate it. So if we negate 0, we get 1. We just get the opposite value. So we have 1 for here again. When P is 1, not P is 0. Over here we have the column for Q plus P bar, or you could call this Q or P bar. The letter V is often used to denote the operator OR, the OR operator. The OR operator yields true when at least one of Q or P bar is true. So we look at the columns for Q and P bar, and when at least one of these values is true, that is 1, then Q plus P bar is 1. So the only time that Q plus P bar is false is when both Q and P bar are false. P implies Q plus P bar yields false when P is true, that is 1, and Q plus P bar is false, that is 0. So when P is 1, as it is here, and Q plus P bar is 0, that is false, then the implication operator yields false, which is 0. Otherwise it is true. So we just put a 0 here and 1s for the other values. Let's look at the distributive property for the operations OR, which is also denoted by the plus sign, or a V like this, and the operation DOT, which means AND, which is denoted by an upside down V sometimes. So we could write the distributive property as P or Q and or equals P or Q and P or R. So we can take the P and distribute it through this set of brackets using this operator here, P or Q and P or R. So this is the other notation, but this notation here, which looks like the notation for adding and multiplying of numbers, does not actually, this relation does not actually hold. If we take any number, say 2, and add it on to 3 times 5, that's not equal to 2 plus 3 multiplied by 2 plus 5. So here P is 2, Q is 3, R is 5, and we have P plus Q multiplied by P plus R. Working this out, we get 17 here and 35 here, so they're not equal. So this particular property is not true for the arithmetic operators, adding and multiplying, but it is true for the logical operators OR and AND. So to see that, we make out a truth table. There are 3 propositions involved. We take one of the propositions, say OR, and we write down its truth values, alternating one at a time. So we write down 0, 1, 0, 1, 0, 1, 0, 1 repeatedly. As a matter of fact, we will need to write it down 8 times, as you'll see in a minute. Then we take one of the other propositions, say Q, and write down its values 2 at a time. So we have 2 zeros followed by 2 ones, then 2 zeros followed by 2 ones. Finally, we take the third proposition, P in this case, and we write down its values 4 at a time. So we have 4 zeros and 4 ones, and that covers all the different combinations that P, Q, and R can have, combinations of truth values that they can have. There are 8 different combinations altogether. That number 8 comes from the fact that we've 2 values for possible values for R, 0 or 1 of course, 2 values for Q, and 2 values for P. So in total we have 2 times 2 times 2, or 8 values for the 3 propositions P, Q, and R. 8 different combinations. So we have 8 rows in this truth table. Now the dot is the AND operator. Q and R is only true when both Q and R are true. That means when both Q and R have values of 1. So let's look at the columns for Q and R, and let's see where they both have values of 1. This should actually be a 1. And if we go down here, we see another situation where both Q and R have values of 1. So this should actually be a 1. In all other situations, Q.R or Q and R is 0. So it's only 1. It's only true when both propositions are true. Now let's look at P plus Q.R, or this means P or Q and R. So this yields true when at least one of these of the propositions P and Q.R are true, when at least one of these 2 propositions are true. So we want the column for P and the column for Q.R. And we put in zeros when the value of P and the value of Q.R are both 0. So we have a 0 here, a 0 here, so we must have a 0. Likewise, we have a 0 and a 0 here, so we get a 0. Here we have a 0, so we get a 0. And for all the other possibilities, we have 1s. So here we have a 0 here, and we have a 1 here, so we get a 1. So if either P or Q.R is 1, then P or Q.R is going to be 1. So it's 1s all the way here, because we have at least a 1 in for the values of P and Q.R. Now we need a column for P or Q, because P or Q comes into this distributive property, and we want to look at the right hand side. That's P plus Q dot P plus R. So we look at P or Q. So again, P or Q is true when at least one of P or Q is true. It's false otherwise. It's false when both of these are false. So P is false here, and it's false here. So we have 0 here. It's false. P or Q is false. Similarly here, we look at the columns for P and Q. Both of these are 0, so we have a 0 here. And for all the other values, we have a 1 appearing at least once in the row. So we have 1s everywhere. Let's look at P or R. Let's just see where P or R is false. It's false when both P and R are zeros, as they are here. So we have a 0 here. It's true here actually, because this is a 0 and this is a 1. And it's false for the next one. We have 0 here, a 0 here, giving us 0 here. And for the other values, it's a 1, because we have 1 appearing here, here, 2 1s here, we have 1 here, 1s here, so we have 1s all the way here. Now we want to AND these 2 columns. We want P plus Q dot P plus R. P plus Q dot P plus R is only true when both P plus Q is true and P plus R is true. So when both P plus Q and P plus R are both ones, then the AND operator yields 1. So we get ones here, and we get zeros up here because we've zeros appearing in these 3 rows here. Now you can see that P plus Q dot R yields the same column as P plus Q dot P plus R. So that tells us that these are equivalent. In this truth table, we're looking at an example of a tautology and a contradiction. We're using the proposition P, which is just 2 values, of course, 0 or 1. We're looking at its negation, not P or P bar, which is got by flipping these values. So when P is 0, not P or P bar is 1. When P is 1, not P is 0. Let's look at P or P bar. P or P bar is true only when when at least one of these is true, which is the case here for both rows. So we've ones here. This shows us that P plus P bar or P or P bar is a tautology because we've nothing but ones in this column. When all the answers are true, then we have a tautology. As distinct from a contradiction, which happens when all truth values are 0. So for P dot P bar, or P and not P, we look at values of P and P bar. Only if they're both true is P and P bar true. So that's not the case here for these 2 rows because we have zeros appearing. So P and P bar is false. So we've nothing but zeros in this column. So that shows us that P and P bar is a contradiction.